Okay, so last time we think this is where we stopped. What arithmetic, which says that every positive integer can be uniquely written as a product of prime numbers. We also looked at this theorem, which says that any positive integer n will have a prime divisor which is less than or equal to the square root of n. So this was the proof. We did that. Now we applied that to some example there. These are the Mersenne primes. So if you can try to, I need to know if you can hear me also. If for some reason you can say that in the chat, there's nobody responding in the chat at all. So I don't know if you can hear me.
I can hear you.
Are you able to write in the chat? Oh, good. Thank you, Bwana Hashem. At least now I can proceed confidently. So today we'll start with this division algorithm. So this one says that if you have two integers, a and b, where d is positive, then you can always find unique integers q and r, where r is strictly less than d, such that a is equal to b plus r. So this r is called the remainder, and this q is called the divisor. The quotient, sorry. B is a divisor. So we are trying to divide A by D. We call D the divisor, Q is the quotient, and R is the remainder. So there are a few things to note here. One of them is we say unique. So these two integers Q and R are unique, but the condition that guarantees they are unique is that R must be strictly less than the divisor. The remainder, if you keep the remainder strictly less than the divisor, then this representation is unique. Unique means Q and R, there's only one pair of Q and R that works for any pair of A and D that satisfy these conditions. So we shall not prove this. It's not really, I don't know why for some reason it is called an algorithm, but it's not quite an algorithm. It just retained its original name. And we followed suit. So here is an example. If you have two integers, say 101, and your divisor is 11, you can write 101 as 11 multiplied by 9 plus 2. So here you have your remainder. This is R. The remainder is 2. And the divisor is R. So this was our D. And the quotient will be 9. Now you notice the remainder must be strictly smaller than the divisor. The remainder can be 0. That's allowed. When it's 0, it means the divisor is a factor of the dividend. So, but it cannot exceed, or rather, it must be strictly less than the divisor. When that happens, it means there's only one pair of Q and R that will work. So here's another example. What is the quotient when minus 11 is divided by 3, quotient and remainder. So for that, we can write negative 11 is equal to 3 multiplied by negative 4. And then the remainder will be 1. So you will notice that we must have the remainder here being strictly smaller than the divisor. So one might be tempted to use negative 3 here, but if you use negative 3 here, you'll have minus 9, and the remainder will be what? The remainder will be negative, right? And we want the remainder to be positive. So for you to get back to 11, you have to subtract 2. We want the remainder to be always positive, between 0 and strictly less than the remainder. So this can work even when our dividend is negative, but we always insist on a positive divisor. So the divisor is strictly positive. The quotient can be negative, that's allowed, but the remainder must be positive. Any questions on that?
Yes, sir. Is there a situation whereby we can
So we can say that A is divisible by B if and only if the remainder is 0 when A is divided by B. So when the remainder is 0, it's quite clear. We simply say A is divisible by the divisor, which is D. So here is another definition. We are defining the greatest common divisor. So that's what we are working on now. So if you have two integers, A and B, and we want at least one of them to be greater than 0, so we can't have both of them being 0. We want at least one of them to be greater than 0. Then the largest integer that divides both of them, divides A and B, is called the greatest common divisor of A and B. So I think this one you're familiar with. And this is a notation. This is a shorthand we shall be using for the greatest common divisor. We shall write the greatest common divisor of A and B simply as GCD of A and B in brackets. So that's the notation we shall use. So the reason we can always find a greatest common divisor is because if the common divisors of any pair of integers will be a finite set, so we can always find the largest one. So previously, when you're getting in your previous encounters with factorization, you used prime numbers to obtain the greatest common divisor. We shall still show how that works, but it's not a very efficient technique because it works very well for small numbers, which is what you do maybe in high school. But when you're in practical cases, you need to look for very large prime numbers, which are not very easy to find. So if you are going to use prime factorization to find the greatest common divisors, then it becomes very inefficient when you're working with large numbers. So we shall look at a better method later, which is called the Euclidean algorithm, which can help us find the greatest common divisor. There are other better ways also. There are techniques that are used
divisor then
in computing that work really fast. I don't know what is happening. I can see people trying to talk, but I cannot hear anything from your end. Okay, so let's look at an example. So this one says, what is the greatest common divisor of 24 and 36? This is easy. We we can easily list the
What
set of
repeat
all
it?
common divisors of 24 and 36. So the set of all common divisors will be 1, 2, 3, 4, 6, and 12. So we found the set of all common divisors. We just need to look for the largest one, and that is 12. This is easy because 24 and 36 are small numbers, so it's easy to list the set of all common divisors, right? So the second example asks us to find the greatest common divisors of 24 and 35. And again, the only common divisor here is 1. So this kind of numbers have a special name. If you have a pair of numbers whose greatest common divisor is equal to 1, we say that that pair of number is, we say they are relatively prime. So we say they are relatively prime. We shall define this later, but maybe I can just write it down. Good. So we say if two integers have the greatest common divisor equal to 1, then we say that the two integers are relatively prime. Now there's also another term that is used, which means exactly the same thing. So you can use either the phrase relatively prime, or you can just call them coprime. So 24 and 35, for example, in this case, are coprime. Okay. I hope that is clear. So this is a definition, exactly what we were just saying before, that two integers a and b would be called relatively prime if the greatest common divisor is 1. And then we have said also some books may prefer to use the word coprime. It simply means the pair of integers have greatest common divisor equal to 1. So here is another example of a pair of coprime numbers, or a pair of relatively prime numbers. 17 and 22, the greatest common divisor is 1. So you can think first of n integers. So we have n integers, a1, a2, up to an. And we can say they are relatively pairwise. They're pairwise, relatively prime. If any pair of integers you pick from this set will have greatest common divisor equal to 1. Pick from this set, the greatest common divisor is what
10. Yeah,
relatively prime. Only 3.
yeah.
So we can check 2 at a time. If you check 10 and if you check 17 and 21, the GCD is 1. So yes, this first set not the GCD is not 1. The GCD is actually 2 for 10 and 24. So that stops this second set from being pairwise, relatively prime. We now look at a technique that allows you to find the greatest common divisor using prime factorization, like primes first before you can do it. And the large primes are not easy to find. So suppose that the prime factorization of zero numbers are as follows. A with the same happens to be, you get the prime factorization. Now you so each exponent is a non-zero integer. Occurring in the factorization of either A and B. Include and sometimes you may have to put zero exponents. I'll explain that. So in some, the reason you can put, you can have all having the same primes is so that you can allow these zero exponents. You will see an example in a minute. But if you have them all the same, then you can apply this technique now to find the greatest common divisor. So the greatest common divisor of A and B now will simply be P1 raised to the minimum of these two exponents, A1 and B1, and P2 raised to these two exponents, A2 and B2. And this goes on all the way. So this now will give you the greatest common divisor of A and B. That's the formula. So I hope I don't know whether the problem is on my end. For some reason, if anyone speaks, the volume is just too low. I can't hear a thing. So are you following up to that point?
Hata hatujasikia kitu.
No.
Yes, sir. Understanding.
Yeah. So this will make sense in a minute. We're going to do an example, but I need you to, if anyone is writing, holding on to the slide so that if there's anyone trying to write, you have enough time to write.
Okay. Okay. Someone is talking, but I can't hear what they're saying. Okay, so now you'll have to just take my word for it now. Hopefully next time the audio will be better. So let's apply this technique here. We want to find the greatest common divisor of greatest common divisor of 120 and 500. So this is a problem we need to solve. Draw. So there. I'm trying to get in here. I've got it now. This is to find the greatest common divisor. 100 and 500. First thing we do is to find the factorization 1 and 5 of 500. Here we have 2 raised to as a prime factor, but does not appear in the second factorization. So for us to put it in our format, we will have to include 3 as a factor here, but we raise it to 0 because 3 raised to 0 is equal to 1, so it doesn't change them. All the factors that appear in 120, the factorization of 120 will appear in the factorization of 500. So that's what we meant by in this statement. We said sometimes we may need to include 0 exponents. We need to include 0 exponents. Yeah. Once we have them in that form, then we can apply our formula. So you will have 2 raised to the minimum of the exponents for 2, which are that's the minimum of 2 and 3. Then 3 raised to the minimum of 1 and 0, and 5 raised to the minimum value for 1 and 3. So we end up with 2 raised to 2, 3 raised to 0, and 5 raised to 1. And the answer is 20. So this is what you have been doing all along, I think, from primary school. Just that you didn't have the formal presentation of this. But this is precisely what you've been doing from primary school and maybe up to high school when finding the prime factors of an integer. So you can try to do this example later on by yourself, and I will send you some exercises as well. Now, the other definition we'll look at is what we call the least common multiple of positive integers. It's simply the smallest positive integer that is divisible by both a and b. So you look for multiples of a and b that are common and pick the smallest possible common multiple. That becomes the least common multiple, which we shall find as follows. So how do we find the least common multiple? Suppose that if you have a prime factorization of a and b as follows, again, using the same ideas so that all the primes that appear in the first factorization also appear in the second. And if necessary, you can put in non-zero. You can put 0 exponents to make them appear in both factorizations. Then you can get the least common multiple, which is down here. So minimum, you pick for each the maximum. For P2, you pick the maximum of A2 and B2 and so on until you reach for Pn, you pick the maximum of An and Bn, the exponents. Configuration, you can we can apply it to this example. It's a simple example. So suppose we have the prime factorization of 2 integers. This is one of them. 2 raised to 3, 3 raised to 5, and 7 squared. Suppose this is the prime factorization of some integer. And 2 raised to 4 and 3 raised to 3 is also the prime factorization of the second integer. Yeah. Again, we observe that there's this factor 7. 7 appears here, but it does not appear on this side. You can hear me?
Yeah.
Good. So it doesn't appear on this side. So for you to complete this, you simply add the 7
Yes.
on this end, but you raise it to 0 so that you have the same factors appearing in both factorization. For these 2 numbers. So the list LCM, this is the abbreviation for LCM. LCM of this first number and 3 and 4, 3 raised to maximum of 5 and 3, and 7 raised to maximum of 2 and 0. And that becomes this 2 raised to 4, 3 raised to 5, multiplied by 7 squared. So there are some books which will do the following. If you have the GCD of A and B, some books will use the following notation. They write the GCD of A and B as they just represent it with round brackets like that. That's how some books do it. So if you find a book that is representing the GCD in this form, that should not confuse you. So some books will just do that. And some will also represent the LCM of A and B with square brackets. So that is notation that is also used. So the LCM of A and B, sometimes some books will choose to represent that as A and B surrounded by square brackets. So if you encounter that kind of notation, you should be able to, the context will tell you what you're dealing with. So here is a theorem, which I will leave as an exercise to you. It says that the product of any two numbers, positive integers, is equal to the product of the greatest common divisor and the least common multiple of the two integers. So anytime you have the greatest divisor and you of a pair of numbers and you multiply it by the least common multiple of the pair of numbers, then you should be able to get this product. So you can prove this in your own time. This is left as an exercise to you. Here, you can use, for you to prove it, you need to use this configuration. This configuration is what will help you to prove it. If you play around with this, you'll be able to see why that is the case. So this definition, along with this definition of the greatest common divisor, if you use these two, you will be able to prove that the product of A and B is equal to the greatest common divisor of A and B. So the proof here will be left as an exercise. So yesterday, the next topic is called modular arithmetic. Before I go to the next topic, there was a question yesterday from a student who said that was supposed to be something you were supposed to prove. I don't know if he has been able to prove it. The question was this. I asked him to go and prove it. I don't know if he has proved it. If A divides B and
A divides C.
B divides A, then the following will be true, that A will be equal to either plus or minus. Is that correct? Or the other way to write it is that the absolute value of A will be equal to the absolute value of B. So I hope you're able to prove it. So maybe they just use a definition of divisors. If A divides B, or rather if B divides A, it means you can write A as a multiple of B. And also if B divides A, or rather if A divides B, then it means you can write B as a multiple of A. So you can work with that. SA, sorry. Just
This idea, and I think in your own time you should be able to prove it. Use a definition of the factors, divisors of an integer, and you'll be able to prove that one. Good. So I'll close this, then we move on to the next topic. If you have a question, maybe you may have to type it in the chat. I really cannot hear, for some reason, I can't hear anything that from your end. There's someone who says my voice is breaking. Can you hear me? Just type in the chat if you can hear me. Well, I don't know what examples you want. I've given examples for everything I have done. I'm not sure what you mean by you want examples. So what you have to learn to be patient in class. You cannot learn everything instantly. So I have to go through the theory and wait patiently for the example. So Euclid's algorithm, we shall go through it later. Not now. It's still part of it's on the menu. So be patient. We shall get there. But what you have to learn is to be patient. So focus on what we are saying. Don't try to, don't bite off more than you can chew. Everything will make sense eventually. So if you get ahead of yourself, you will not understand anything. And don't expect to understand anything instantly. Most of this is just simple English. If you put in a little effort, you will be able to understand it without any examples. But I'm still giving examples. So don't be afraid. Everything is going to be just fine. So don't give up even before we start. Wait patiently, the examples will come. And now you have to, like I told you, you're not in high school anymore. You have to be able to read something like this and try to create your own examples out of this statement only. So now going into mathematicians. These are things now you should be able to teach. So you need to understand them very well. And that means you have to have the patience to go through all these statements. Be able to create examples by yourself, because what I'm teaching you is a very small part of mathematics. Eventually, there are lots that you will have to read on your own, and when you're reading on your own, there's nobody to create examples. You have to start practicing now. So we'll talk about modular arithmetic. Let me see if there are any more questions.
What?
There is someone called Michelle who is making noise for us. I think she has muted now. Otherwise, I'm going to, if you make noise, I'm going to send you to the waiting room. So let's quickly define this. I was invited to be a judge for this HALT prize, and they're starting in about at exactly 9. So I might stop a little earlier. So what we'll do is I don't know if any of you are participating. Hopefully you are. But I'll quickly, I'll just start off this with the definition, then we can do more of this next week. So let's start here. If A and B are integers and M is a positive integer, so we don't care what the signs for A and B. All we want is that let's see if I can make this clear. So we don't care the sign for A and B. It can be anything you want. We're more interested in M being a positive integer. So M must be a positive integer. So we make the following claim that A will be congruent to B. So A is congruent to B modulo M if M divides the difference, A minus B, right? And then we shall use this as a notation. If A is congruent to B modulo M, we shall use this as a notation. We shall write it as A with this identity sign. This means A is congruent to B modulo M. So what this means is that A minus B is divisible by M. So in a situation where A is not congruent to B modulo M, then we shall write, this is how we shall write it. We shall just write A is not congruent to B modulo M. So we just use the same sign, but we cross it out to mean A is not congruent to B modulo M. So remember this, for congruence, we are using 3 parallel lines. It's not an equal sign. So you don't write equal means a totally different thing. We are using congruence. So there have to be 3 parallel lines when you're writing this notation. Let's see if there are any questions. So someone says we send PDF notes. These notes have been sent to the WhatsApp group. I think maybe you are not paying attention to the notes in the WhatsApp groups. The notes are already shared. I think I shared them last week. So talk to your class rep. Class recordings, I will send the links to the class reps also. So, and we have only had one. So be patient, you will get them. So now pay attention in class also. Don't be jumping for recordings fast. You're already in the class. So give it as much attention as possible. So you only go back to the recording when you are stuck. But if you make good use of your time in class, you will not need to go back to recording so many times, unless you need a clarification somewhere. So make the best use of the time you're in class. Okay, so we look at some examples now to illustrate this. So this first example is asking us to check if 17 is congruent to 5 modulo 6. This annotation thing, let's draw. Yeah, got it. So we want to check if 17 is congruent to 5 modulo 6. So remember we say that A, the definition says A will be congruent to B mod M. So modulo M, if what happens? This is only true if M divides the difference, A minus B. So if M divides A minus B, then that works. So you have to keep this definition in mind for you to be able to answer the questions. So let's check. We want to check if 17 is congruent to 5 modulo 6.
That means we need to check if the difference between 17 and 5 is divisible by 6. So 17 minus 5 is what? It is 12. There we have it. So 17 minus 5 is 12, and 12 is divisible by 6. So 6 divides 12, and therefore we can comfortably say that 17 is congruent to 5 modulo 6. So make sure you get these definitions correct, because we shall be using this very frequently. And if you don't understand these definitions, they will not be making sense. So let's check the second one. We have 24 and 14. Is 24 congruent to 14 modulo 6? That is what we want to look at. So the question is 24 congruent to 14 modulo 6? Again, we do the same thing. Just get the difference between the two numbers, 24 and 14. The difference is 10, but 10 is not divisible by 6. So since 10 is not divisible by 6, we conclude that 24 is not congruent to 14 modulo 6. So that gives the definition of congruence. So the mathematics that is done around this kind of stuff is what we call the modular arithmetic. It's highly applicable. Even the computer actually runs on this modular arithmetic. And a lot of cryptography depends heavily on this modular arithmetic. Cryptography is just how you ensure your message are transmitted safely without interception. So this mathematics is what runs encryption. So my suggestion is that I stop here so that I can go and become a judge for the business proposals which are starting in about 9 minutes. So I don't know if there are any questions. I'll have to check the chat because for some reason I cannot hear. I can hear, but it's very low, the volume from your side. So I have just explained what modulo is, what we mean when we say modulo. So I don't know what Levi wants. So Mohammed, if you have anything that you don't understand, please come get a group of people who are having the same problem, or even if it's just you, come to my office and ask the question.
Well,
Mohammed, are you okay? If you have any problem, please. It's easy to find me in my office. Or you can just inform the class rep or even inform me, and we can arrange for a additional explanation if you need the help.